In this video, we're going to derive the steady-state equations to calculate the initial flow rates of two spherical tanks, derive the differential equations to solve for the time variation of the fluid in both tanks, and we're going to write the code that goes with it. So, both spherical tanks are open to the atmosphere, they have inlet and outlet flows, and they're connected by the bottom by a pipe and have different fluid heights. The radius of R1 is 4 meters and R2 is 2 meters. The pipe's area, which is A12, is 0.2 meters squared, and the area of the pipe that drains the second tank is also 0.2 meters squared, and it's denoted as A sub 2. So the problem is that at t equals 100 seconds, the flow to the second tank is reduced to 80% of its initial steady state value, and at 200 seconds, the flow to the second tank is increased by 250% of its initial steady state value. So here are some things to keep in mind. The volumetric flow rate is equal to the velocity times the area, and in this case, the area is the cross-sectional area because the flow rate is what we're looking for, and we're given that the cross-sectional area is 0.2 meters squared. And here is Bernoulli's equation. It is the change in pressure plus the density times volume squared divided by 2 plus the density times the acceleration due to gravity times z. And that is our height of the fluid relative to a point, and that's equal to 0. Our points in this are represented as the circled numbers 1, 2, 3, and 4 down at this bottom. And the fluid pressure is rho gh, and we'll be substituting this equation in for pressure, which is P in Bernoulli's equation. So it's now the change in density times acceleration due to gravity times the height plus density times velocity squared over 2, and that's plus density times acceleration due to gravity times the height of the fluid relative to our point equals 0. We're going to rewrite the delta symbol in terms of the varying heights in velocities. So we'll get rho times g times h2 minus h1 plus rho times v2 squared over v1 squared, plus v1 squared over 2 plus rho times g times z2 minus z1 equals 0. The additions just represent change in height, change in velocity, and the height of the fluid relative to our point. So in this equation, all three rows will cancel out, and the z2 and z1 are equal 0, so they're equals to each other since z1 and z2, which represents point 1 and 2, are at the same level in our diagram. So I'll cross out this entire term because multiplying by 0 just gives you 0, and I'll cross that out. And so V1 is equal 0 as well because the area in tank 1 by point 1 is much larger than the area located at point 2 by the pipe. So we can expect the fluid at point 2 will move, but at point 1 it's going to be insignificant because the movement at the fluid won't be moving because of the no-slip boundary condition. So now we're left with G times H2 minus H1 plus v2 squared over 2 equals 0. So rearranging this to solve for velocity, which is what we need, we get v2 equals the square root of 2g times h2 minus h1. So now we'll write the flow rate between tank 1 and tank 2, which will be denoted as Q12. So we get Q12 equals the square root of 2g times h2 minus h1, and this is multiplied by A12, which is the cross-sectional area. The h2 and h1 were switched because h1 is visibly higher than h2, and we want a positive number. So now we need Q2, which is the first equation written as the volumetric flow rate that's equal to the velocity times the cross-sectional area. So rewriting our equation in terms of tank 2, we have rho times g times h4 minus h3 plus rho times v4 squared minus v3 squared over 2 plus rho times g times z4 minus z3 equals 0. This is the density times the acceleration due to gravity times the difference in heights of the pipes, plus the density times the difference in velocities at point 4 and point 3, and this is divided by 2, and then we add the density, multiply it by gravity, and times the difference between the heights of the fluid relative to our points that we're looking at. Again, the rows will cancel out. Z4 and Z3 are equal to 0, so we'll cancel that out too. And we'll cancel out that G2. And the V3 squared cancels out as well for the same reason that the velocity is insignificant compared to V4 because of the no-slip boundary condition. And so, furthermore, the H4 in our equation is also going to equal 0 since the pressure is going out of the system and into the atmosphere. So I'll cross that out as well. Rewriting this, we will get negative G H3 plus V4 squared over 2 equals 0. And then we're going to rewrite our equation to solve for V4, and we get V4 equals negative the square root of G times H3 equals 0. And H3 is is located at 0.3, but its height is actually H2, and that's equal to 3 meters. And so I'm just going to erase this H3 and replace it with H2. And so then plugging this equation into our flow rate at point 2, we get Q2 equals the square root of 2G times H2, and this is multiplied by A2, which is the cross-sectional area of the pipe, which is equal to 0.2 meters squared. So we have derived the equations for the initial flow rates of the two spherical tanks. These are Q1, 2, and Q2, right here and there. And now I'm going to erase all of this and keep what's important and bring us back to deriving the differential equations that solve for the height of the fluids at any given time. Thank you. So now that we're back, we're moving on to deriving the differential equations to solve for the time variation of the fluid height in both tanks. To do this, we're going to focus on the volume of the tanks, and please ignore these diagrams because we'll get to them eventually. So tank 1 has a change in volume over time that's equal to the sum of all the flow rates. So I'm going to write this now and explain after. So we have dV1 over dt equals Q1N minus the square root of 2G times the absolute value of H1 minus H2. And this is multiplied by A12 with sine with respect to H1 minus H2. So the flow rates we have are Q1, and that's positive since it is entering the system up here, and Q12, which is connecting both of the, or A12, which is connecting both of the tanks, and it's negative, and it's because it's leaving tank 1. So yeah, Q12 is this one right here, and this is multiplied by A12. And this is the velocity times the cross-sectional area, and we have absolute values because we don't want imaginary numbers. So we have this sign variable in there in the case that the fluid in tank 2 is higher than tank 1, and this makes sure that if H2 is higher than H1, we'll get a negative sign, and this can be seen in our diagram because the liquid would be flowing from tank 2 into tank 1 if it was higher. So moving on to tank 2, we have Q2, which is positive, Q12, which is positive, sorry, and Q2, which is going out of tank 2, so it'll be negative. So we're going to have dV2 over dt equals Q2n plus the sine of H1 minus H2 times the square root of 2g times the absolute value of H1 minus H2, and this is all multiplied by A12 and minus the square root of 2g H2 times A2. This is the change of volume with respect to time equals the total flow rates experienced by a tank 2. Now we need the change in heights, so we're going to put these equations into terms of height. So I'm just going to write this right in front of the equations that we derived. So in our first equation, and sorry, this is pretty tight, this is equal to a1 times dh1 over dt, and this one is similar. The dv2 over dt equation is equal to a2 times dh2 over dt. So this is saying that the cross-sectional area of the tank that we're concerned with times the change in height relative to time is equal to our equations that we're deriving. So solving for these, we'll divide a1 and a2 over the equations that we derived, but keeping in mind that our tanks are spherical, the cross-sectional areas are going to change. So now we're going to look at this diagram of our spherical tank. We have point 0 at the bottom, and our height is represented h of t, or h with respect to t, because the height of the fluid will be changing due to the flow rates. And r is the radius, and the horizontal line is the representing the fluid, and the line connecting the center of the sphere and the horizontal line is the radius of that specific time. The vertical line that represents, or that creates another triangle, represents the distance from the normal radius. And this diagram shows a closer look, and so the horizontal line is the radius from the center of our circle to the height of the fluid, and it's denoted as RT, since it's our radius at time t. The vertical is HT minus R, and this is the height of the fluid at time t minus our normal radius. Using these, the Pythagorean theorem and the area of a circle to solve for radius at time t, we need to have two equations. Our Pythagorean theorem equation will be r squared equals r of t squared plus h of t minus r squared. Our area of a circle equation is a equals pi r squared, and we want to know the radius at any time. So we end up getting this equation after rearranging. We have r of t equals the square root of r squared minus h of t minus r squared, and this is the radius squared minus the height of the fluid at any time t minus the normal radius squared. So now we want to solve for the cross-sectional area of these tanks. So we have A equals pi times r of t squared. Square rooting this, we end up getting pi times r squared minus h of t minus r squared. So plugging this into our two long equations right here, we get dh1 over dt equals q1 in minus sine h1 minus h2 times the square root of 2g times the absolute value of h1 minus h2, and this is multiplied by a12, and this is all over pi times r squared times h of t minus r squared. This is essentially saying that the change in height with respect to time is equal to that dv1 over dt divided by the cross-sectional area that now has an equation. The cross-sectional area equation are the same for both since they're both changing and are dependent on the height of the fluids. So to clarify, we have this all over our cross-sectional area since the cross-sectional area times the change in height over time is equal to the change in volume over time. This is our first differential equation. So we're going to do almost the exact same thing with the second equation. So we get dh2 over dt equals q2n plus sine of h1 minus h2, and this is multiplied by the square root of 2g times the absolute value of h1 minus h2, and this is multiplied by a12, and then we have minus the square root of 2g h2, and all of this is equal or over pi times r squared minus h of t minus r squared. And in this equation, the sign is positive because the pipe is entering tank 2, right here. And these are our differential equations that solve for the time variation of the fluid height in both tanks. Thank you.